Calculus of polar points, day one. You need to know these things. You learned them in previous classes. Moving along. Find the rectangular equations of the tangents at the tips of the petals for r equals 2 sine of 3 theta. So I have this graph over here that has 2 sine 3 theta. Notice that that only goes from 0 to pi and then it starts repeating itself. Okay, so if I take the derivative of r equals 2 sine 3 theta, I get 6 cosine of 3 theta. And notice um, dr d theta equals 0 when the line is tangent to any circle. Okay, so in this particular case, it's tangent to the circle r equals 2, but any circle r equals a, if we have a line that's tangent to the circle, then dr d theta is going to be 0 because the radius is not changing at that particular point. And that's what we're finding. We're finding dr d theta is 0. So at that particular value of theta, r is not, r's change is 0. So then we continue to solve and we get 3 theta equals pi over 2 and 3 theta equals 3 pi over 2 because that's where cosine of 3 theta equals 0. So then we have these values. I'm trying to hide these things because if I write it while I'm talking, this video will take like an hour. So I'm trying to get everything settled and still hide things from you. So these 6 values of theta end up working out from 0 to 2 pi. Now remember that this function is graphed entirely from 0 to pi. So I really only have to use pi over 6, pi over 2, and 5 pi over 6. I don't have to use the other 3 values. However, when you look at the graph, pi over 6, 5 pi over 6, and 3 pi over 2 are actually the values that you see. Pi over 2, 7 pi over 6, and 11 pi over 6 aren't. Now, if you're looking at 3 pi over 2, notice that it does hit it at pi over 2, but it's going in the negative direction. It would be r equals -2. So that's why we see it as 3 pi over 2. So that's why we're going to use these 3 values and not these 3 values at the bottom. So these 3 values at the bottom we're going to treat as repeats and we're not going to use them. Okay, so all of these will occur at r equals 2. Notice that that's true about the graph, and that makes sense because all of these values of theta make 2 sine of 3 theta, where sine equals 1. So that makes some sense. So now we must find the normal line. And when you think about this, all of these blue lines we have here are normal to this line. So they're normal to the line that goes from the origin, r, and is like r. I know I shouldn't have said is like r, but they're normal to r at the petal. Okay, so that's kind of what we're looking for. So what I did was I drew one of these little petals, and then I figured out that since this one is at pi over 6, the slope of r there is up 1 and over root 3 from the origin here. So that means the slope is 1 over root 3. So the normal line is going to have an opposite reciprocal slope. So that's negative root 3. And notice that the point rectangularly is x is root 3 and y is 1. So I can write that as a rectangular equation. I can repeat that process for the other 2 petals and I get these 3 answers. So just showing you on Desmos that that's actually what happens, and we kind of get a cool picture with a triangle and the petals. Problem 2. Find the vertical and horizontal tangents to r equals 1 minus cosine theta. So the slope of the tangent line to a polar curve is given by this formula. And I'm going to prove it really quickly using parametrics. So we'll take x equals r cosine theta and y equals r sine theta, and then we'll replace r with f of theta because that's what it tells us to do. So I use the product rule and I do dy d theta over dx d theta, and I end up with that. So basically what we have is this derived using parametrics. It wasn't that complicated. All right, so now the problem that they ask us to do is r equals 1 minus cosine theta. So we'll treat that as f of theta equals 1 minus cosine theta. I graphed it over on the right. So horizontal tangent lines. Horizontal tangent lines occur when dy d theta equals 0. Let's think about why that is. If we are plotting a, uh, a graph in polar, something will be horizontal if as theta is sweeping around, my change in y is 0. So that's going to be probably around here and around here. Okay, so those are likely our situations where we're going to have horizontal tangent lines. Our job now is to figure out the theta values where that works. So we basically just do a bunch of algebra. Replace f prime with sine and f with 1 minus cosine, because that's what happens when I take the derivative and plug in the actual function there. And then I just do a lot of algebra, a lot of algebra, a lot of algebra, factor, set equal to 0, realize that that works at 0, 2 pi over 3, and 4 pi over 3. So those horizontal tangent lines that I drew were at 2 pi over 3 and 4 pi over 3. Um, Notice at 0 something weird happens. We have a cusp, so we'll talk about that in a minute. Um, Try and hide that one. Also notice that I had a green arrow kind of showing up here. That's because, get out the way. Okay, good. So notice I could have, instead of changing sine squared into 1 minus cosine squared, which is a trig identity, and I didn't really explain it very well, so that's my fault, from sine squared to 1 minus cosine squared. That's something I did. The other thing you could have done was used a different trig identity. You could have taken negative cosine squared plus sine squared, factored on a negative sign, and realized that cosine squared minus sine squared is actually cosine of 2 theta, and you would have got the same answers because cosine theta equals cosine 2 theta at exactly 3 angles between 0 and 2 pi. It's at 0, 2 pi over 3, and 4 pi over 3. Okay, now let's deal with vertical tangents. So it's the same process that we have going on. F prime cosine minus f sine, that's what dx d theta is. There is a lot of algebra that is to be done. So I just replace f prime and f with what they were. I have 2 sine cosines, so I replace that with 2 sine cosine. And then I can either factor, which will show up on the left, or replace um, I can replace my function I can replace 2 sine cosine with sine of 2 theta. That's another trig identity that you learned in Algebra 2 and pre-calculus. So I could do either way. I could factor and get these 4 answers, or I could replace this with sine of 2 theta and realize that sine of 2 theta equals sine theta at those 4 same values. Okay, so if I were looking at this graph and I were graphing vertical tangent lines, it appears that I have 2 of them again, and then 0 is kind of a weird case. So notice I have 2, but this one intersects the graph twice, so that would make sense why we have pi over 3 and 5 pi over 3 as answers. Um, Now, the last question is, what about theta equals 0? And theta equals 0 makes some sense that horizontal and tangent, or horizontal and vertical, both give us 0, because it looks like we end up with a cusp. And when we have a cusp, something weird happens, which, if we're looking at dy dx, which is dy d theta over dx d theta, we got 0 over 0. That's kind of caused some chaos. So that means that it may not necessarily be a vertical tangent line, and in this case, it ended up being a cusp. So if we look at the graph, I'm actually going to plot um, all of our tangent lines there. And what I'm showing you here is, with this purple one, I get x equals 1/4. I could have written it as x equals 1/4, but I wanted to show you that if I plot x equals 1 minus cosine of 5 pi over 3, or I could have done pi over 3 and cosine of pi over 3, I end up getting x equals 1/4. And notice what's happening here is x parametrically is r times cosine of theta. So if I actually want to find the rectangular uh, vertical tangent line, I would make x equals r times cosine of theta. R, remember, was 1 minus cosine theta, and I ended up getting it. Y, instead of writing 3 root 3 over 4, which is exactly where this is, I could have written it as R, which is 1 minus cosine of theta, and remember, one of my thetas was 2 pi over 3, times sine of theta, 2 pi over 3. And so I end up getting the exact same thing, which is 3 root 3 over 4. I could do the same thing with 4 pi over 3, and I'll end up with the tangent line that is on the bottom. So that's how writing them in rectangular works. Problems 3 and 4. Area in polar coordinates. It is kind of important to understand that area in polar coordinates is discovered the exact same way that we got area in rectangular coordinates. We basically treat it like it's infinitely small rectangles, and then we add them up, and the limit of that sum is what we call the integral. Well, instead, in polar coordinates, instead of there being rectangles, they're actually infinitely small sectors of a circle. So the sector of a circle, the area formula for the sector of a circle is pi r squared, which is the area formula for a circle, times whatever the angle is over 360 degrees. That was something you actually learned in geometry. Now we're going to continue, instead of using 360, we'll now use 2 pi, since radians are way better for our purposes than degrees. And then we do a little calculation. Pi divided by 2 pi ends up being 1/2, and we get 1/2 times r squared times theta. Now notice, if we're taking a bunch of thetas, so basically what I want to do is I want to make this infinitesimally small, so make the angle super small. That's how it becomes a d theta, and we're just going to sum all of them up with an integral. So I have 1/2 times the integral from alpha to beta, and alpha and beta are two angles that we're dealing with. So it's 1/2 times the integral from alpha to beta of r squared d theta. This is something you have to memorize. So you have to memorize 1/2 times the integral from alpha to beta of r squared d theta gives you area in polar coordinates. Okay, problem 3. Find the area in the plane enclosed by the cardioid r equals 2 times 1 plus cosine theta. So since cardioids have 2 pi as their period, or how long it takes to cycle the whole thing, we're going to go from 0 to 2 pi, and then 1/2, and then I'm finding the area of this. So this is my r, and I'm going to square it. Now it's just a bunch of algebra. So I'm going to show you the algebra relatively quickly, but 1 plus 2 cosine theta plus cosine squared. Then cosine squared, I used one of the identities at the beginning to turn it into 1 plus 2 cosine, or cosine 2 theta over 2, and then I separated the parts. 1 plus 1/2 is 3/2. And then I just integrated. So I integrated all of these parts, and then I multiplied the 2 in, and then I plugged in 2 pi and 0, and I got 6 pi minus 0 minus 0 plus 0 plus 0 plus 0, or whatever, and I end up with 6 pi. Find the area enclosed by one petal of the rose curve here. Well, actually, I should probably go back to this. Oh, I actually really didn't need to do that at all, because there was nothing all that exciting about that problem. Okay, problem 4. Find the area enclosed by one petal of the rose curve. So I'm going to go from negative pi over 4 to pi over 4. And the reason why I'm doing that is because that is one petal of the rose curve. So if I went from 0 to pi over 4, that would be the top. And if I went from negative pi over 4 to 0, that'd be the bottom. So when I add them together, I get one whole petal of the rose curve. So 3 squared is 9. I'm moving the 9 out. I'm using cosine squared of 2 theta, and I'm using an identity for that. And then I'm going to move the 1/2 out. So that's how the 9/4 is going to start showing up. So 9, stop it, 9/4 times theta. So notice that after I move this 2 out, it's 9/4 times 1 plus cosine of 4 theta. That's where that comes from. And then cosine of 4 theta's integral, or antiderivative, is 1/4 sine of 4 theta. So now I'm going to substitute stuff in, and I end up with um, 9/4 times pi over 2. Now, the thing in green is actually kind of interesting. So, what we're finding is that I just found this area. But if instead I find the integral from 0 to 2 pi, that's tracing it from 0 to 2 pi. That's essentially finding this area plus this area. And notice that that should be the same area. And I did a little calculation of that, and it ends up working out. So that's good. If we go from 0 to 2 pi, that actually does the exact same thing, and the numbers are pretty easy to calculate. So that means that if instead I do 0 to 2 pi instead of negative pi over 4 to pi over 4, I still get the same answer. It uses symmetry to get what I need. Problem 5, find the area inside the cardioid and outside the circle. So if we look at picture number 1, there's both drawn together. Um, and then what I'm really trying to do is I'm trying to find this area. So the area inside the cardioid, but outside the circle. Now notice what that means is that means that I have to find basically the area of the whole cardioid and then subtract 2 parts. I have to subtract the area of half of the circle, and then I also have to subtract the area of this section of the cardioid. So those are the 2 parts that I'm subtracting. This part of the circle over here is irrelevant for our problem. So once again, I'm subtracting half of a circle and one little section of a cardioid. So basically what we have to do is we have to figure out where these points intersect in terms of theta. This point is at pi over 2. So I'm going to subtract the pi from 0 to pi over 2 of the circle, and then I'm going to subtract from pi over 2 to pi of the cardioid. So just recall that the area of the entire cardioid, we did this in problem 3, the area of the entire cardioid is 6 pi. So I'm going to take the area of the entire cardioid, then I'm going to subtract the area of this half circle, which is from 0 to 2 pi, 1/2 times the integral from 0 to 2 pi of 2 sine, I forgot to write the squared, my bad, minus 1/2 times the integral from pi over 2 to pi of the cardioid. So that's the red section. Really, this is just a semicircle of radius 1. And from problem 3, we know that that integral is 3 theta plus 4 sine 2 theta plus 1/2 sine 2 theta. And that'll make our lives way easier instead of recalculating everything. So since this is really just a semicircle of radius 1, that's pi times 1 squared over 2. And this, I'm going to substitute in pi and pi over 2 instead of doing, instead of recalculating the integral. Since I already did that, we're going to do a little simplification there. And I end up with 4 pi plus 4 is the area that is just green, not the area that's blue or red. So that's taking the whole thing, subtracting the blue, subtracting the red, and we end up with the green. So that is how that one goes. Once again, do a little Desmos. So what we're doing here is we are taking this and we want to find the area of the whole thing, which means we're going to subtract the blue and the red, and we end up with just the black. Okay, now, final problem. Find the area inside of 3 times 1 plus cosine theta and outside 2 sine theta. Recall from yesterday's notes, or the last time you watched notes, Uh, these two things were actually done in a problem that we've already done, and they intersect at theta equals tangent inverse of negative 12 fifths, which is theta is like negative 1 point something, and then we added pi and we got 1.965587. I could have kept more decimal places, but didn't feel like it. So that point is there. Just keep that in mind. So first thing we're going to do is we're going to find the area of the whole thing, so the area of the entire red, and then we're going to subtract a couple things, and we have to kind of figure out how to do that. So um, 9 halves times this integral. Recall that that integral is 3 theta plus 4 sine 2 theta plus sine of 2 theta over 2. We're going to evaluate it from 0 to 2 pi, and we end up with 27 pi over 2. Now, what I have to do is I have to figure out what I'm actually subtracting. So let's go here. And what I actually have to subtract is I have to subtract the semicircle from 0 to 1.9655, whatever that is. So notice I'm getting rid of that right now. And then the other thing I have to get rid of is the cardioid from wherever that intersection is to pi. So that is the cardioid from that intersection to pi, 1.9655, whatever it is. So that is the part that I have to subtract. So 27 pi over 2 is the whole red. Now I have to subtract these two parts in order to get what I want. So now I'm going to subtract the integral from 0 to 1.965587 times 1 half of 2 sine theta squared. That's the circle. And then this part over here is the part of the cardioid that goes from here over. So when uh, part of the circle, part of the cardioid, and then I just did these on a calculator and I found them to be 2.32 and 0.429. And then when I subtract them from 27 pi over 2, I get 39.662.